So now we are moving to forces in machining. Normally we are seeing the introduction to machining process, so we deal with only the orthogonal. So first we should know what is the need of studying the forces in machining operation. If you see, the knowledge of cutting forces is required to estimation of the power requirements. Normally power requirements, if you see, it is Fc into V. So if you can calculate the cutting force and you know the velocity, cutting velocity, so you can calculate the what is the power required or the energy required. For the machine tool design, that is the static and dynamic stiffness, what is the stiffness required, and based on that you can design the tool. Normally the machine tool are designed like lathe bed and all those things are designed with the material cast iron, because the cast iron has a graphite in it. So graphite will have the damping effect. Okay, so you in order to have the damping and all those things. Okay, for that purpose also it will be useful. What are the forces that the lathe bed or the cutting tool, at the same time tool holder, tool post, these are all to be designed. So if the forces exceeds, what will happen? So in order to be safe, the machine tools are designed according to that. For that purpose, one has to calculate the forces required. Okay, part accuracy and the tool work deflections. So the part accuracy is also important. If I can calculate what are the forces that is experienced during the machining by the tool, and if there is any deflection of the tool, if the deflection is there, then there will be problem. So the part accuracy goes bad. So for that purpose, one has to calculate the forces. Okay, so to maintain the no deflection or there is a minimal deflection, one has to calculate the forces in the machining operation. Okay. So there are the forces in orthogonal metal cutting, that is the machining processes. Force acting in three locations. One is a shearing zone. If you see the shearing zone, that is nothing but the shear force and a normal to the shear force. This is a shearing zone. Okay. So the chip tool interface, the other forces that one observes in this region is the chip tool interface. Normally there are two forces, one is the frictional force and normal to the frictional force. These two are there in this forces on the cutting tool by the workpiece. Normally Fc and Ft are what one can experimentally measure, is these are the Fc and Ft. Okay, these two forces are the forces experienced by the cutting tool. Normally this cutting tool is placed on the dynamometer, so the dynamometer will give the forces. Okay, so this the third one, this is what the forces that one can measure, and the 1 and 2 are calculated from the experimentally measured forces, which we can see in the upcoming slides. Okay. So if you see, there are three force components in a metal cutting operation. One is cutting force, second is the thrust force, and the radial force. These are the three forces. Normally the cutting force tangential to direction, it is also called as a power component. Normally this is, as I said in the beginning of these forces, Fc into V gives me the power requirement. That's why this is called power component. And the cutting force normally acts on the tool by the chip. Okay. So I will explain. Once I explain thrust force and radial force, I will come back to the cutting force, how the cutting force will act. The thrust force, it acts in the direction of the feed, that is axial direction. That means in this picture, if you see, this is the thrust force. Okay. So my feeding direction is this, that is nothing but the workpiece axial direction also in this direction. So this is the feed direction. This is the radial component, which is also, you can see, it has a radial direction. That means as per the depth of cut is concerned, it will move in this direction. So this is called Fr and this is called Ft and this is called Fc. That means whenever I am cutting with the cutting tool, my chip is moving on top of it. If that is case, my chip will kick down the tool. That is nothing but the cutting force. That means that it will be in this direction. So the cutting chip, whatever the chip is coming out, it will kick the tool downside, that is the cutting force, and along the direction or the axial direction of the workpiece, that is called the thrust force, and or the sometimes some people they call as a feed force also, and the radial force is nothing but as per the depth of cut is concerned, it will be radially inside into the workpiece. Okay. So, the forces F, that is frictional force, normal to the frictional force, shear force and normal to the shear force, these are all not calculated directly. Okay. These are all measured from a relation, force relation, that is which we will see in the upcoming slides, which is nothing but the merchant circle relation. Okay. The forces acting on the tool, that is nothing but the cutting force and thrust force. Also the other forces, if you have a dynamometer of which two components, you can measure Fc and Ft. Nowadays you also get the three-dimensional measurement of the cutting forces. So, where you can get the third component also, that is called radial component also. So, normally if you see how to measure Fc and Ft. Okay. So, that I will discuss in the next slide. These are all can be written in the cutting force. So, only that we can measure using the dynamometer is Fc and Ft. So, if we know two forces and different angles, tool angle, that is rake angle, shearing direction and all those things, that is alpha, the friction angle beta, if you know the shearing angle phi. So, with these relations you can calculate the frictional forces, shear force, frictional force, normal to the shear force, normal to the frictional force, these are okay. That means these are all measurable. Okay. From the merchant relation, merchant circle relation, you can calculate all these Fs, frictional force, shear force, other things. Now the question is how to measure and how one can measure this cutting force, thrust force. Just we are seeing in the orthogonal, that is why we are only dealing with the two forces. Okay. So, the force measurement, if you see the force measurement, normally this is the dynamometer, you can see, which is located beneath the tool. This is the tool, this is a tool post, this is the tool post, or the tool holder. Okay, you can say this is the dynamometer. Dynamometer is the beneath the tool. So, this dynamometer, inside the dynamometer, if you see the anatomy of the dynamometer, normally to explain you, there are three piezoelectric sensors will be there. Normally piezoelectric sensor works on if there is a deformation, it will give certain voltage or EMF. If you give the EMF, normally it will deform. That is the principle of the piezoelectric materials. So, piezoelectric materials are oriented as per the X, Y and Z axes. So, whenever if you mount a tool on top of it, normally a tool is mounted, and if you are giving some forces in different directions, what will happen? The piezoelectric materials that are there inside it, okay, these are the inside, what will happen? This will deform. Whenever these deform, this will give certain voltage, or the microvolts or nanovolts or some volts, it will give depend on the forces. So, these forces, if you are measuring in three directions on the cutting tool. So, the forces that is acting on the cutting tool you are measuring, that means you are going to get only cutting force, thrust force and radial force. Okay. But normally we see only two forces. However, if you have a three sensors, you can measure the three forces. Okay. This is about the machining process. The same thing can be represented here also. Normally machining takes place at the workpiece like this, and the chip will work on this one, and the radial force will be in this direction. So, normally it will be in the opposite direction also. Okay. As you can see clearly, note that practically measured the forces are Fc and Aft and Fr. These are the practically measured forces. However, from here, using the merchant circle relation, you can calculate other values. Okay. So now we will go for the merchant relation, how to calculate, because how much shear force is required to shear the material and all those things is required, because we are only seeing the cutting force, but we want to calculate what is the frictional force, what is the shear force and all those things, so that we can say how much is useful energy that we are imparting to the machine and how much is going as a waste, and all those things can be calculated. Okay. So to have the merchant circle relation, we are going to have some of the assumptions to measure these forces. These assumptions are: cutting edge is too sharp, that means that sharpness radius is 0. Okay. Normally, slightly some people will have doubt what is this sharpness radius and what is the, see, some people they understand that sharpness radius is nothing but the nose radius, but there is a slight deviation between the sharpness radius and nose radius. Okay. As I already explained, normally if you see a 3-dimensional tool, the 3-dimensional tool looks like this. Okay. So okay. So the nose radius is this one. This is called nose radius, which is represented by R. This is nothing but, if assume that this is my principal cutting edge, just for understanding purpose I just erase the nose radius. Hope you understood. So now what I mean to say, this is my flank face, this is my rake face, which are meeting at the principal cutting edge. This is the principal cutting edge. Every cutting edge will have certain radius, that is nothing but the sharpness radius. How sharp this is, that means this is, if you meet, this is the radius, this is nothing but the sharpness radius. Okay. So nothing in this world is 100% or 0, that means the sharpness radius is practically, it cannot be 0, but however we are assuming that this is 0. Okay. So hope you understood the difference. The difference is, this is nothing but my sharpness radius, whatever the radius that is generated on the cutting edge, this is my nose radius. Okay. So assuming that this one. So the second point is, cutting edge is perpendicular to the cutting velocity, that means that I am doing orthogonal machining. So deformation in 2 dimensions, no side flow, that means that only the deformation is taking place in the plane where we are machining. So there is no side flow or deformation and all those things. Continuous chip without BUV. So the chip is flowing on the rake surface is without BUV. That means that it is a continuous and smooth cutting operation. Workpiece material is rigid, perfectly plastic material. That means that the material is removed perfectly. Okay. So there is no slip or something. The coefficient of friction is constant along the chip tool interface. That means there is no variation in COF, that is cutting friction is constant. If friction is X, that means that throughout the chip tool interface it is constant, because we have the 2 zones, one is a sticking zone, another one is a sliding zone. So practically speaking, there will be a slight difference will be there in the coefficient of friction between the sticking region as well as the sliding region. However, we are assuming it is constant for the this model. So the resultant force on the chip, that is R1, is applied on the shear plane is equal to opposite and collinear to the resultant force. That means that 2 forces that is acting in the directions, both are opposite in direction and collinear in the same direction. Okay. So now we will move to the forces acting in the cutting tool. Since we have already seen in the previous slide, so there are the forces. If you see, this is the shear force and this is the normal to the shear force. The resultant is this one. Okay. Similarly, if you see here, it is in the red color, so you may not see properly. So that this is the force acts parallel to my rake face is nothing but the frictional force. perpendicular to will be the normal to the frictional force. At the same time, you have the two forces, that is nothing but one is the cutting force, another one is perpendicular to the cutting force, that is the thrust force. Okay, so this is called Ft. As you can see, since it is red in red, so you can see the frictional force normally follow as per along the direction of the rake surface or the chip flow direction, interface of the chip flow and the tool rake surface, and perpendicular to will be the normal force normally. So at the same time, two forces, if you see that cutting force and thrust force, these are the two forces that acts on the tool from the workpiece. So these two can be measured. So you can see all the forces here, the frictional force and a normal to the frictional force, and this is called frictional angle, the shearing angle along the direction of the shear. And I will explain you how to draw this merchant circle. This is the cutting force and the thrust force. So you can see the resultant, and normally this is shearing angle, and if you drop, this is called alpha, that is called rake angle. Okay, this is the force acting on the cutting tool during the two-dimensional cutting. Note that all the resultant must be R. The resultant force is R, which is equivalent to the resultant of all the forces, that is frictional force normal to the frictional force, cutting force, thrust force, shear force normal to the shear force, all boils to be resultant is only R. Okay, that is what the assumption is. Okay, vector addition of the frictional force normal to the frictional force resulting in R, that is the resultant force. So vector addition of shear force normal to the shear force gives rise to the again R, and the force acting on the chip must be balanced. For that purpose, R is equivalent to R. R must be in opposite direction to the R. So R dash must be collinear with R. So this is what you can see. So now you can see the same picture here, the merchant circle, where merchant is the person invented it and all those things. The need for force relations to calculate the coefficient of friction, the normal stresses and the shear stresses, as I said in the previous one. So I will let you know how to draw simply. Okay, so the merchant circle is a circle. So merchant circle, normally just first you draw a circle. So normally it should be on the upside. So normally the tool should be above the central point. Okay, so you can take any position and you can draw the tool. So this is the point. Now your frictional force is parallel to this rake surface, and your cutting force is parallel to the cutting direction, that is the cutting velocity direction, and you are shearing in this direction. Okay, so this is my, so I know frictional force, the cutting force and shear force, just three directions. So I can choose any. Now normally the thrust force is perpendicular to it. So the resultant is R, which you have seen. This is nothing but R. This is my thrust force. So R will connect to R. So this is nothing but my N. So this is my frictional angle beta. This is the shearing angle, that is phi. This is alpha, that is rake angle. So from the geometry or the trigonometry and all those things, you can calculate other angles. If you see like this is also become alpha, as you can see here, these two alternative angles, and this is the phi, that is a shearing angle. This is the beta, which I am already explaining you, that is the frictional angle. If you take this is 90 degrees, so 90 degrees equal to, so alpha plus some other things which you can boils out to be beta minus alpha here. Okay, so and this will be 90 minus beta. Okay, so if alpha plus 90 minus beta, this angle is then you can calculate this angle plus x, assume that x. If you can calculate, now your x will be like beta minus alpha equal to x. So that is nothing but this angle. Okay, so this is how you can calculate all the things. So that's how my x which I want to calculate is beta minus alpha. The coefficient of friction, the first thing what we are going to calculate from this one is the coefficient of friction. The coefficient of friction is nothing but tan beta. So this is my beta angle, tan beta equal to F by N, that is mu. This is coefficient of friction that I am going to calculate. So the normal stress is Ns by As, which is Ns is nothing but this normal to the shear force to the area of shearing. So shear stress is nothing but my shear force by the area of shear. So this is how you can calculate. We are going to calculate these three from the known sources, because Fs we don't know, because we know Fc and Ft. From this, using merchant circle, we have to calculate Fs, Ns and frictional force as well as N. So that's why we are going to calculate all these things. The total work done is nothing but your Fc into V. Okay, so Fc into V equal to shear force into shearing velocity and the chip velocity into the frictional force. These are the, this is useful energy, this is unuseful energy. Okay, assume that I can say it is a energy going as a waste. Okay, so now we will calculate all these things. So what do you need to measure the coefficient of, why, what is the need? So if you want to know what is the answer for this one, what is the need of measuring the coefficient of friction? So if I want to if I can measure coefficient of friction, that is nothing but my this one F by N, so that I can understand what is the energy going as a waste, that is nothing but what is the energy that is going here. If I can calculate coefficient of friction, normally coefficient of friction is frictional force by normal to frictional force, that is proportional, directly proportional to my frictional force. Okay, this one. If my coefficient of friction is very high, that means that my unuseful energy is very high. So the useful energy goes down for the same input energy. Okay, that's why we want to calculate the coefficient of friction. Now if you see from the geometry, tan beta, that is nothing but F by N, tan beta, this is the beta, tan beta is F by N, this is opposite side by adjacent side. Now I want to calculate what is the F. See, what I always said in the previous slides also, I don't know what is the F value, what is the N value, but from the dynamometer, what can I measure is cutting force and thrust force. Okay, so whatever I want to calculate, I have to form the triangular notation to the joining to the Fc or Ft. For that purpose, what I have did is F equal to AB. Normally this is A, this is B, F equal to AB. If it is AB, which is I am dividing into AC plus BC. Okay, AC plus BC. Now AC I am connecting like this. This is a triangle that is called ACM triangle. From this triangle, I can say that Fc sin alpha, that is called, this is alpha. From the trigonometry you can get, this is it comes as a alpha. Okay, so this is Fc sin alpha and Ft cos alpha. BC is Ft cos alpha. Now see, BC is equal to dn. Okay, dn, this is alpha this is the triangle that is called MND or DMN. This is the triangle, which in this triangle, this is my alpha. So it is called Ft cos alpha. So at the same time, I have to calculate again normal to the frictional force, that is called N. This dB, which is called BD or dB, which is equivalent to NC. This is called NC. Here is N. Just let me erase so that I will come back again. Now NC equal to MC minus Mn. MC is nothing but this one. MC is this one. MC minus Mn. This is Mn. Okay. So now MC is connected to my cutting force, this force. So Fc cos alpha, which is adjacent to this one. That's why it is Fc cos alpha minus Ft sin alpha. Okay. Now Ft sin alpha, because I am talking about Mn, which is opposite side. So Ft sin alpha. So now we have known values, that is called Fc is known to us, rake angle is known to us, Ft is known to us, because Ft and Fc are measured and alpha is the rake angle. Here also Fc and Ft are measured and alpha is the rake angle of the tool. So now I can calculate the frictional force as well as normal to the frictional force. If I know the frictional force and normal to the frictional force, I can calculate the coefficient of friction. This is the final term, that is called Fc sin alpha plus Ft cos alpha by Fc cos alpha minus Ft sin alpha. This is the final equation where all are known to me and I can calculate coefficient of friction. As I said, if my mu is high, my useful energy will goes down, that for the same input energy. That means that my frictional force into chip velocity will goes up. So that means that unwanted or waste of energy will be more. Okay. So now we will see the normal stresses on the chip. Normal stress is equivalent to Ns by As. Okay. So Ns, if you see the Ns is nothing but this is my shear, Fs is shear force and perpendicular to is Ns, this is Ns. Okay. Now I am dividing Ns, that is nothing but the dP is nothing but normal to shear force. So I will divide into two things. One is already I have one Q is there. If you see in the picture, dP I am dividing into dQ plus QP. So dQ, which is relevant to, as I said earlier also, I have unknown things I have to correlate with the known things, that is Ft and Fc. So that I have to form my triangles. If I can make the triangles, that is integral part of one should be known, that is Fc and Ft, so that I can calculate. So now I am going to say dq is equal to, now I say dq, this is dq and I know this is a phi. So this is the adjacent side to this triangle DMQ, so that it can become cos phi. So Ft cos phi. So plus at the same time QP. Now my QP is there. QP is equivalent to MO. If you say MO, I am forming a triangle AMO where I know the phi is the shearing angle in this triangle. For that purpose, MO is equivalent to my QP. So this is opposite side to this triangle AOM to the phi. That means FC sin phi. So area of shear plane, if you see, B into TC. Now if you see the bottom picture, this is nothing but my TC, which is not known to me because I have not measured it. But considering the two-dimensional metal cutting, that is orthogonal metal cutting, T naught, that is called uncut thickness, and chip thickness are the after cutting and before cutting. So after cutting, T naught is equivalent to my feed, Okay, if I know feed, normally I will give whenever the cutting operation is going to start, I have to give feed to the machine tool. Okay, so this T naught is known to us, TC is not known to us. That means that this is unknown to me, and B is nothing but my width of the chip or depth of cut. So area of uncut thickness is nothing but B into T naught, and now we have to find the relation between T naught and TC, that is uncut thickness to the thickness. As if you form a triangle, so T naught is this whatever I have drawn here. If you take this as a triangle, this is the phi. So you can calculate from this triangle T naught equal to TC into sin phi. Okay. From that, now we don't know what is the TC, and if you put this equation 1 and 2, if you put equation 2 in the 1, normally you will get equation 3. Okay. So now you can put this into the above equation, that is ns equal to this equation. Okay. So now you can calculate sigma equal to this value, that is called fc sin phi plus ft cos phi by multiplied by sin phi into a, where this is a is nothing but your depth of cut multiplied by uncut thickness, that is nothing but the feed. Okay. So since we know the depth of cut and feed, area of uncut thickness can be easily measured or calculated. Okay. So now we are going to the shear stress on the chip. Now the shear stress is nothing but the Fs by As. I already seen what is As, that is the area of the shear plane. Okay. Now we have to calculate Fs. So Fs is nothing but this one. So this is about AP. Okay. This is nothing but my Fs. Okay. Considering this, now I am making a extension to the O, and I am saying now considering the AOM triangle, if you see that one, AO minus OP gives me Fs, that is PA. Okay. AO minus OP. So now AO, which is shearing angle, that is adjacent side. So you can say FC cos phi minus OP. Now OP is equivalent to this MQ. Okay. MQ, I know this phi, so that is opposite side. So that means that if this is FT, this is opposite side sin phi. So FT sin phi. So we can from this again from the previous slide, these are all same, where area of the shear plane is nothing but B into TC, which is where the TC is not known, and the area of uncut thickness is nothing but B into T naught, where T naught is the feed, B is the width, that is nothing the depth of cut. So depth of cut is known and feed is known. So you can know this value. You know this value. Okay. So now from this one you can say AS equal to A by sin phi. Whenever you put back this into the equation, that is a shear stress equation, you will get the shear stress is nothing but this one. Okay. That is FC cos phi minus FT sin phi multiplied by sin phi by area of undeformed chip, that is nothing but, which is nothing but your depth of cut multiplied by feed. Okay. So from the orthogonal metal cutting operation, if it is oblique metal cutting, normally there will be some other terms also will come, because there will be a slightly inclination will be there, and all those things will come into the picture. Okay. Since we are studying only the orthogonal metal cutting operation, this is how you can calculate the shear stress. If you know the shear stress, normally you have to apply the more energy compared to the shear stress, then only the material will shear. Okay. So that means that whenever I want to shear a material, I have to put more stress than the required stress, then only the plastic deformation will takes place. Severe plastic deformation will takes place. Work done in specific cutting energy. So now work done, total work done is Fc into V. As I already said, the cutting force multiplied by the cutting velocity is the total work that is done during the machining operation, or that I am imparting, that is the energy. Work done in shear, that is called useful, and work done in friction, as I said, coefficient of friction is calculated or frictional force is calculated and all those things. So now total work is Fc into V, and which is divided into useful and as well as waste energy. Okay, this is the main equation. Now coming to the, if my friction is more, what will happen? My unuseful energy or the waste energy will goes up. So my whatever the input I am giving, the most of the energy goes as a waste. So I always should think in the sense where how to reduce the friction, and for that purpose only the people uses cooling fluids. That is what our course also deals about, is machining fluids. At the same time tool coatings are done, lubrications is done, different types of lubrication is done, like minimum quantity lubrication, flood lubrication, or cryogenic lubrication and all those things, so that my this factor F into Vc will go down, so that my useful energy, if I am giving Fc into V, so I have my main aim is to increase this Fs into Vs. So these are the alternatives, the cooling and all those things, so that my useful energy goes increases for the same input Fc into V. Okay, so that's about the useful. Okay, now coming to the specific cutting energy. So specific cutting energy is nothing but the total work done or the energy given to the volume of the work piece material removed. Okay, that is nothing but Fc into V, specific cutting energy, normally represent in terms of U basically. The specific cutting energy is nothing but energy given to the material removal rate. Okay, how much is removed per unit time volume. Okay, that is nothing but my chip thickness, that means uncut thickness into the, this is called my feed, this is called my depth of cut, and this is called my cutting velocity. Okay, so if I use, this is mm, this is also mm, and this is mm per minute or second. So now you will get is material removal rate. Okay, that is about the specific cutting energy. Some people will calculate it in other way also. Now we are moving to the velocity relationships. Velocity relationship, as we know, there are three velocities in the machining. One is chip velocity. Now you can see the chip, for the betterment of understanding, we have the chips are there. Assume my chip velocity will be the direction of my frictional force. At the same time cutting velocity will be like along the direction of this one, that is nothing but V, this is nothing but Vc, and the shear velocity will be in the direction of shearing. Okay. Okay, so now you can see this velocity V is cutting direction. Just I am telling you the directions only because my machining is taking place, and the shearing velocity, you can see here also shearing velocity is taking place, and my chip velocity is moving in this direction. Okay, so shear velocity with respect to cutting velocity will have phi, this is known. So rest all the things we will see in the next slide. Okay, assume that the work material is moving against the cutting tool with velocity V, that is the cutting velocity. The surface plane that shears is AB, that is what I am saying. This is the plane, shearing plane, which is nothing but the Vs. In other words, as I already said that chip velocity is there, cutting velocity and shear velocity. The chip velocity along the tool rake is the vector sum of the cutting velocity and the velocity discontinuity along the shear plane. As I said, velocity discontinuity, what I mean to say is that whenever there is a discontinuous chips, that is what they are specifying. Okay, so the bottom line of this slide, what I want to say is the chip velocity, that is nothing but the Vc, this Vc, okay, along the tool rake, vector sum of the cutting velocity and shear velocity. This is the cutting velocity and this is the shearing velocity. Okay, what they say is sum of Vs is equivalent to Vc. Okay, from the cutting, if you see from the geometry of the machining, we have already seen the angles. This is shearing angle, and we know this is 90 minus, because this is the rake. If I see the rake angle, for that purpose I have to draw like this is my alpha, so this is my 90 degrees, so 90 minus alpha. So this is, if I know this is 90 minus alpha, this is phi. Now I can calculate this as a 90 plus alpha minus phi. Okay, so this is how we have divided into that one. So if you can see clearly, for understanding purpose, this is the phi, this is 90 minus alpha, this is 90 plus this phi minus alpha minus phi. Okay, so from the sine rule, what we can understand is the side of this one to the opposite sine of that angle, that is nothing but Vc by sine phi, and V, that is nothing but this one cutting velocity, by sine 90 minus phi plus alpha. So another one is Vs, that is nothing but Vs by 90 minus alpha, sine 90 minus alpha. So it gives rise to V by cos phi minus alpha, because 90 is there, so here cos there, and here also 90 minus alpha is there, so Vs by cos alpha equal to Vc by sine phi. This is the relation, and from the relations you can calculate in terms of this Vc by V. Normally Vc by V, some people in some textbooks you can also say as chip thickness. It is correlated to chip thickness also, like a chip reduction ratio or chip thickness ratio. They can be calculated like this also. Okay, now we are going to calculate what is the shear strain. The shear strain, that is the deformation related to the original size. Okay, so that is the material undergoes as explained as possible, that is nothing but the gamma. So gamma is nothing but AB by OC. So this is the triangle ABC, and where we know the phi, this is the one. So now taking the triangle, enlarging here, now ABC is the triangle. I am just dropping a perpendicular to the AB, so that I can, this angle is phi minus alpha. From the geometry, just it is a simple geometry you can calculate, as we have also seen this is the phi, so alternate angles, so that will be also phi. Now we know the angles, this is phi and this is phi minus alpha. So if you see AB by OC is nothing but my shear strain, that is nothing but AB, this is AB by OC, this is the what will, now AB you divide into AO into OB, so divide by AO by OC plus OB by OC, which gives rise to cot phi plus tan phi minus alpha. This is the final equation, which is equivalent to gamma, that is shear strain. Okay, so this is about the shear strain. Now we will move on to the shear zone models. So what are the shear zone models? So there are many shear zone models, like thin zone model, thick zone models, and all those things. However, since this is an introduction course on metal cutting and machining fluids, so since we are there in the machining, so we only deal with very primitive model. For understanding better models, you can go through the textbooks, or you can register for the next upcoming course, which is on mechanics of machining by some other professor from IIT only. So they are going to teach you the mechanics of machining, where they will take you to the completely into the mathematics spectrum of this machining processes. Anyhow, I will come to that slide also and all those things. Okay, so there are thin zone models and thick zone models. Okay, so the thin and thick zone models, so normally idealized model, the orthogonal 2D cutting with a well defined shear plane, also called as a merchant model. This is called a thin zone model. Primary shear zone is a line basically. Okay, You can see in a thin zone model, this shearing is a line, okay. But in the thick zone model, it is valid for only high depth of cut and feed when the low speeds. This is thick zone models are valid. Normally thick zone model, you can see there is a area, okay. So that is the difference between thin zone model and thick zone model. But practically speaking, thick zone model is not considered, because if you see, it is only valid when there is a low speeds with high depth of cut and high feed. Normally the cutting operations may be done using these input conditions. However, in the general practice, basically this may not be used. That's why, for a better understanding purpose, we are going for the thin zone models. As I already said you, thin zone model, let me summarize. This thin zone model is a line, and the thick zone model is a plane, or it is an area, okay. So that is the difference between a thin zone model and a thick zone model. So we are going to see only one thin zone model, that is where the shear angle relationship that can be drawn, that is the Ernest-Marchant theory, okay. So the first assumption is shear stress is maximum at the shear plane and it remains constant. That is nothing but the shear stress is maximum and it is constant, okay. The second important point which I want to emphasize is the second point, that is the shearing action takes place in the direction in which the required shearing energy is minimum. That is nothing but, not this one, Fc into V is not the 0, here it is the derivative of Fc into V is should be 0, okay. So our Fc, both are approximately similar. So now the Fc and Fs, these are all are measured. So from the Fc is nothing but cos beta minus alpha. Now Fc is this one. So Fc, you can say now in terms of R, this is the resultant one, cos beta minus alpha, okay. This is adjacent side to the ADM triangle. For that purpose, this is this one, and now Fs equal to R cos phi plus beta minus alpha. So now Fs is this one. So now you can say I have to include another phi, so that it will give. Now Fc you are writing in terms of Fs, so I can write now Fs, since we know Fs is nothing but shear stress is nothing but the shear force is nothing but the shear stress multiplied by the area. So in that circumstances, you can see the shear stress multiplied by area, shearing area. So the shearing area is already given here. From that we can say now Fc equation, if you incorporate this equation in the first equation 1, what will happen? You will get this equation 2, okay. As from the point number 2 or the assumption number 2, the shearing action takes place in the direction in which required shearing energy is minimum, okay. From this point, if you understand, that is nothing but shearing action. So the derivative of shearing energy along the shearing direction should be 0. That means that derivative of Fc with respect to the shearing angle should be 0, okay. Now you saw, if you do the derivation of this one, you will get this is a big equation that you can see here, which you will get. From that you just say is equivalent to 0. From the cos equation, you will get this cos phi plus beta minus alpha equal to 0. Normally when cos angle is at certain what angle it is 0, normally pi by 2. So that means that 2 phi plus beta minus alpha equal to pi by 2. So cos, okay. So now 2 phi equal to plus alpha minus beta, or if you take the minus outside, what will happen? Pi by 2 minus beta minus alpha. These two, if you are sending this direction, So it will gives raised to pi by 4 minus 1 by 2 beta minus alpha. So that is what the shearing angle relation is here. Okay. Okay. So this is about the one model only. Now the question is why I am not touching many models. As I already said that there is a separate course delivered in the MOOCs on, just I want to give the glimpse because there is a specified course on mechanics of machining, which is the advanced course of pertaining to this course by IIT Guwahati professor. So you will see in this semester, in this one or the next one you may be. Okay. So I am not going in deep mechanics, that is not going into deep of mathematics dealing with all these things. So I am restricted to myself because this is the introductory course to the machining. So I will deal only certain part of the machining as well as the machining fluids. Okay. So if at all you are interested to go into the deep mathematics, the conversion of the angles, NRS system, some of the things that I have not discussed is like NRS system, MRS system, angle conversions, at the same time thick zone models, thin zone models, what is shear deformation and what is a severe plastic deformation and all those things, and the mathematically other professor is going to deal. So you can register to that one. That course is called Mechanics of Machining, that is courtesy to IIT Guwahati. So IIT Guwahati Center for Education is going to bring you this course in the upcoming semester. Okay. The summary of this is what the cutting forces in the machining process is done. The cutting force measurement, how using dynamometer and all those things, and the merchant circle to the calculate various forces. We know the FC and FT. From there we have calculated Fs, Fn and normal to the shear force and all those things. Coefficient of friction, that is we have calculated. Shear stress, normal shear stress, and shear rate also we have calculated, that is shear strain rate. The velocity relationships that we have, and thin zone models we have done, even though the thick zone models are there, which you can see in the upcoming one.